Hi everyone, my name is Paris. That's me on the left, not the right, in case you were wondering. I come from the Wellington of Australia, which is Hobart, Tasmania. It looks a bit like this, which I think is actually quite similar to Wellington. It feels very similar in lots of ways. And every time I tell anyone that I come from Hobart, they're like, oh, you're from the Wellington of Australia. And every time someone comes here from Hobart, they're just like, why did I bother coming here? But I actually love Wellington. So I'm really, really glad to be here. It feels very much at home. I write a lot of books, I build video games, and I also work on a tool called Yarn Spinner, which is not related to this talk even slightly, but people seem to like it. Today's talk is about kind of three things. That was a bad idea. Today's talk is about three things. It's about Unity, which I don't like their new logo, so I decided not to use it. It's not very good, right? It's about PyTorch, which is a Python machine learning framework that you may or may not be familiar with. And it's about a Unity package called Unity ML Agents, which is one of the many things that Unity tends to throw at the wall to see what sticks. So they may abandon it next week for all we know, but right now it's really interesting and really cool. In this session, which is a similar session to one I've given many times over the years at various game conferences, or this is a kind of a new version, we're going to talk a little bit about what machine learning is. We're going to talk about how Unity ML Agents works with machine learning, which is that package that Unity provides. We're going to make a little bot, which is the actual purpose of Unity ML Agents, and we're going to talk about why this is useful. So I might have time for questions. Sometimes my rehearsal kind of ran with 5 minutes of questions. Sometimes it didn't. We'll see. I could also speak really fast and just go through the whole thing in 5 minutes. So we'll find out together. We're going to start with the basics of ML. So if any of you are like ML gurus, I apologize. I am not an ML guru. I am just a game developer that discovered that it's really fun to play with machine learning. So I do not have a maths background or machine learning background. I just like playing with it in the context of my game development career and my game development skills, and I think you might too, which is why I'm here. So I might completely munge some of these descriptions of how machine learning actually works. So if anyone actually knows what they're talking about, please feel free to correct me later, because I would appreciate that. But basically, machine learning is about learning patterns from data. It's about figuring out how something relates to other things. It's about linking a specific set of data to another specific set of data. So you might give it a whole bucket of stuff and ask it to classify it based on something you've taught it how to do. So you give it a whole bunch of examples of the things you want to classify, and then it learns to classify those things based on those examples. This is where you get like the dog versus cat thing you may have seen examples of, and it's also where you get lots of machine learning failures, like where if you give it a very specific shape, it thinks it's something that it's completely not. So there's this great example where if you give it a really shiny disk picture, like a thing that looks kind of like a chrome disk, it thinks it's a toaster no matter what, just because toasters are kind of shiny in chrome. And sometimes machine learning, when it looks for patterns, looks for really stupid things. So it looks for things like, we've had examples where there's been machine learning running on satellites where looking for like tanks or things in war zones, and they've thought it worked perfectly, but instead of finding a tank, it's found like the tiny cross in the corner of the picture that like the software that's monitoring the satellites adds when it's taking a picture of a war zone, versus the thing that when the cross is not there, there's no tank. When the cross is there, there's a tank. So the machine learning learned that to find the cross to decide that there was a tank, and didn't actually learn anything about tanks. So machine learning will just learn what you give it. It will not actually make sense of anything. It will just try and make a pattern out of what's there. And sometimes it sees patterns that you don't. So it's really important to remember that machine learning is not magic. It's not actually intelligent. It's just making patterns. There's one specific kind of machine learning called reinforcement learning, which is the one we're going to be looking at today. That's basically linking actions to feedback. So instead of linking all the things you're giving it to some sort of label or classification, you link it to the thing you want it to do. So you're basically generating rules based on observing your environment. So the gist of reinforcement learning, RL, is you can't describe all the rules you might want for something to operate. So if you wanted to create an agent or a bot that had a whole bunch of rules by which it operated, you could either code them manually, which is basically what traditional video game AI was, sometimes called heuristics, just a list of rules, or you could let the bot go kind of nuts with random behavior and then reward it when it accidentally does something similar to what you want it to do. So eventually it will happen upon doing the right thing in every situation because you've taught it based on reward signals what you want it to do. And that way you can kind of generate very realistic, reasonable, interesting behavior, or completely useless behavior, without having to write a massive set of rules. So I'm going to give a quick example now. This is a video, so hopefully the sound works. It's a colleague and friend of mine, John, and another colleague and friend of mine, Tim, acting out a little scenario to show you how reinforcement learning works very quickly. So if the sound doesn't work, we might have to backtrack. Nope, okay.
Might walk forward.
Have a minty.
Thank you. Oh, brilliant. Oh, I might take a step backwards.
Give me that minty back.
Guess I'm walking forward.
Have a minty!
Hey!
So John, the guy in the lab coat, is the agent here. He is being attempted to reinforcement learn to go forward. And the reinforcement positive signal is he gets a minty. Do New Zealanders know what a minty is? Is that the thing here? Sorry, sometimes I do this talk in America and I'm like, they give a minty. And the American's like, what is a minty? Can you tell us what that is? Or I use a really specific candy. So minties here? Minties are good. Okay, good. That's good to know. Regionalisms are really important when you talk, right? So people know what you're talking about. John gets a minty when he goes forward, and when he goes backwards, he got the minty taken off him. He was never told which one was bad, which one was good. But theoretically, he's got like a notebook, which you might call a policy, and we'll get to that in a second, that he writes down when I get a when I go forward, I get a minty. And that's how reinforcement learning works, but at a really, really fast scale and lots of repetitive actions at once. So the goal of RL is for an agent, in this case John, to learn a policy which correctly maps the inputs it gets to the correct responses. So basically he's trying to figure out what to do at all times based on the rewards and the senses it has of its environment. Reinforcement learning has a training phase where basically it learns about its world, takes actions, either randomly or based on some other policy. For the sake of this talk, we're going to stick with random. It's much easier to understand that the agent is essentially just doing random things in the world until it kind of converges on something that makes sense. And it gets a reward based on something you've defined when things happen. So if it does something that kind of gravitates towards what you want it to do, it gets a reward. If it does something negative, it gets a negative reward. We still call it a reward because machine learning is slightly weird like that. So it's like a minus or a positive number. It's basically just number go up, okay? So reinforcement learning is really good for sequential decision making, and it's commonly associated with robots. And now robots have a lot of similarities with entities that exist in video games. So, and you might notice I'm kind of alternating between agent and bot. Same thing as far as I'm concerned. And again, an agent is learning a policy, and a policy is a mapping from what it observes to actions. Observations are what an agent can know about the environment it's in. So when I say observations, it's tempting to conjure up something that's seeing or watching or hearing. It's not necessarily that, it can be that, but it's more often than not like, I am on grid coordinate 1, 4, or whatever. Or sometimes it might have extra information that it doesn't sort of visibly have. So if you're thinking of a video game character, it might know the position of the player as an observation, just like a true fact, so it can move towards it as necessary. But it doesn't necessarily have full knowledge. It might though. So agents learn their policy by rewards. When you train an agent, that's when it learns its policy. Rewards can be positive or negative. And a good policy learning is basically trial and error. It tries something, it gets a reward or a negative reward, it tries again and go on. And it's slowly converging towards only getting positive rewards. Hopefully that really quick introduction to machine learning and reinforcement learning made sense, because now we're going to look at this in the context of using it with Unity. So the Unity package is called ML Agents. It's available on GitHub. I'm not going to show you how to get it. Hopefully we all either know how to use Unity packages or can learn that, because I think the more interesting thing about this talk is looking at it rather than learning the nitty-gritty of Unity. Here's how ML agents works in the context of reinforcement learning. Basically, an agent perceives something within a scene using observations. Observations are a specific thing that ML agents gives you the capability to add. So you can use your code, you can add observation, or you can add a component in Unity, which is an observation. There's all sorts. I'll show you some of them shortly. ML agents basically makes a decision. In the case of training, it makes a random decision within the scope of what you can give. Like you can create basically a control harness for the agent. So if it's a car, it might have your standard car controls. If it's a human, it can move around, whatever. It makes a decision within the scope of what the agent can do and sends it to the agent. The agent does it, and it's rewarded or penalized accordingly, and that just repeats constantly. So in ML agents, there's some components which should sound familiar based on what you've heard about reinforcement learning. There's an agent, there's an environment. Environment's probably a Unity scene, or one scene might have multiple environments in it. The agent has actions it can do, which are probably something in code that lets it move around the scene, although not necessarily. The agent collects observations about the environment, which are probably lines of code you've given it that say, you know the value of this variable. And it collects rewards, which are literally you're saying set reward based on certain things happening. So an example of John a minute ago, the agent is Dr. John. The environment is a park in the middle of Hobart. His actions are step backwards, step forward. Maybe he can turn as well. His observations are his own position along that line and the position of Tim, who is giving him the minty. His rewards are he gets the minty when he goes forward, and he loses the minty when he goes backwards. So eventually you would hope that John would converge on a policy of going forward, maybe towards Tim. Does that make sense to everyone? Does that seem reasonable? Okay, let's take another look at another example. This is a Unity example that they like to show off a lot, and I like it as well. This is a cube. It's a cute cube. It exists in a formless void. Its actions are it can kind of rotate, and its observations are its own rotation and the position and the velocity of the ball that sits on its head. So it gets a reward of like 0.1, a very small reward every step of the game simulation that the ball remains on its head. And it loses a very large amount if the ball falls off. So this is ideally going to learn a policy where it will basically keep the ball on its head by jiggling appropriately. I'm going to take another quick couple of looks at these and then we'll actually look at some in Unity. So this is another environment. There's another cute cube up there. Its environment is a small arena with a goal. It's the green area. It can turn and it can move, or it can do nothing. And it has a bunch of raycasts, so raycasts can be observations within the Unity engine, and it can see the wall and the goal, and it can see the block. So it gets a very small negative reward every step, which is basically designed to economize its movement. We're trying to make it do whatever it needs to do as quickly as possible with as minimal steps as possible. And it gets a very large reward when it pushes the block into the goal. So eventually this thing will converge on getting that block into the goal. And then it's very quickly just going to zip around that arena and push the block into the goal. It's exactly what you want it to do. You can get more complicated with this. This one has some memory in that it knows the order of things. So eventually this one will learn to count upwards by ramming itself into the numbers in sequential order. I'm not going to read through all the details on each one. But you can do complicated behavior. And this one can do that because it knows whether a tile's been visited or not, and we start penalizing it if it visits them out of order, so it eventually learns how to deal with the order as well, which is kind of cool. You can make it quite complicated. You can make things that look like they're animated but are not. This is a spider-looking thing. It can rotate all its joints as its action, but it is not otherwise animated. There is no rigged animation here. It has observations for the position, rotation, and velocity and angular velocity of all of its limbs. And it knows the acceleration and angular velocity of the body and the position of the cube it's trying to get to. And basically it gets rewarded every time it's pointing towards the cube and heading towards the cube. So it basically chases the cube around the arena and kind of learns to walk. You can kind of look at this from the lens of robotics as well, which is pretty cool. This is a robot arm and it basically tries to pick up a cube. So it's often helpful to think about this in the context of the real world, because I think one of the reasons Unity ran this program is because they kind of like to diversify from games, and I think they were trying to get into like automotive simulations and stuff. But this is also really fun for game developers to play with, which is why I like talking about it. And of course, you know, the Terminator makes sense in the context of this. The Terminator is the agent, and its environment is Earth. It can do pretty much anything. It has all sorts of observations, and it gets a reward when it kills any human, and a big reward when it kills a specific human, right? So hopefully that makes sense. So in Unity, an agent is any game object that has a component type of type agent. Basically, it's not a mono behavior anymore, it's an agent. And then it has access to all the things it needs to be an agent. An environment is the scene the agent is in. It doesn't really have any specific concept of an environment unless you need it to. Its actions are whatever options you put in the agent's choose action function. So you override a specific function and say, this is how this agent moves. And its observations are whatever observations you send into ML agents. And again, the rewards is whatever you say. So let's have a look in Unity. I'm going to do this live because I'm a masochist, and why not? You know, I've got 2 straight months of conferences. Why not start it with a live demo? So we're going to quit this for a second. I'm going to push this button and go mirror. Now you can all see my secrets. So this is Unity. You may be familiar with it. Let's hope you are. This is a little environment that I made earlier, which is based on one of Unity's demos. I'm going to just quickly give you a tour of this environment and then explain what's going on in here. So this is a floor. There's nothing special about it. It's just a plane. Okay? This is a cube. Absolutely nothing special about this either. It's just a cube. So I've placed a cube on a floor in Unity. That's it. I've grouped them together in an area that I've just named area. Again, the area does nothing special. And I've created a sphere to be the agent, which is here. Okay, the agent is where the magic happens, as far as I'm concerned. The agent is just a sphere that's sitting on the floor, but it's been given this ball agent script, which I've written. So we're going to have a quick look at the ball agent script. I'm not going to get too much into the programming side of it, because I don't want to spend all the time doing stuff that's not super interesting, but you can figure it out yourself. Let's make that a bit bigger. In here, we've just imported the ML agent stuff, pretty standard C# Unity stuff. We've descending from agent instead of mono behavior, also fine. This is not very interesting, but here we have onEpisodeBegin. So onEpisodeBegin is one of the things we override to be an agent as far as part of ML agents. In here, basically, if this agent falls off the world, we reset its position. That's pretty standard. And we randomize the position of the cube that it's chasing. So the goal of this agent that we want it to converge on is we want it to roll the ball somewhere where the cube is, okay? Its observations are collected here. So this is where we send those This is where we send those observations into ML agents, which is by overriding a collect observations method. And this method, basically we can say, we have however many sensors we want to have, and we send those observations right into Unity, which passes them on to the Python underneath. So in this case, we are sending an observation for the position of the target, which is the cube, and we are sending an observation for the position of it, which is the agent, and we're also sending the velocity of its rigid body. So that's the only information the machine learning system has to work with. It doesn't know anything else about the world. Here's onActionReceived, which is where the ML system sends those random actions in during training. Basically, it can roll. That's all it can do. If it gets close to the target, it gets a very large reward, which is that set reward 1. If it falls off the platform, we end episode, which basically starts the training process again. We've also got a heuristic method in here, which Unity ML Agent supplies, which lets us drive it with a keyboard just to test. It's very hard for machine learning to control something inside Unity, inside a game world, if you can't control it as a human. So it makes sense to make a control system that you can use to test it out. So if you can't navigate the world very well, then the agent will probably have trouble as well. That's literally all the code we have. Hopefully that makes a little bit of sense. It's assigned to this thing. So that's over here. And we've assigned that cube as the target, so it knows what the cube is. Then we've added a decision requester. This is a component that comes with ML agents. It basically says you can request decisions from ML agents. Those decisions in training will be random, and in inference, which is the phase when you actually have a learned brain, a learned model, will be based on the policy. So the decisions are the thing that directs the agent how to move. And then we have a thing called behavior parameters, which basically says your behavior name is ball, and you have the following observation. So it's got a vector space size of 8, which is those vector observations we sent in earlier about its position, the target's position, and the velocity. And it has 2 continuous actions, so it can roll on both axes. Currently it has a model assigned, which is something that I've given it because I trained it last night to show you one working, but I'm going to show you how the training process works in a second. So I'm going to delete that from the slot there. So if I run this right now, Unity might crash because it does that. Okay, here we go. So if I run this right now, you can see I can kind of roll this ball around with the WASD keys, and when it falls off the edge, it resets, as does the cube. Sorry, that camera's not in a very good position. That's better. Yeah, so, yep, does that make sense to everyone? And if I hit the cube, it'll disappear and go somewhere else, because I'm succeeding. But that's just me controlling it. So if I wanted to train this, I need to give it some parameters to train. That's something called hyperparameters. It's from the machine learning field. The hyperparameters of this scenario are not very interesting right now. We haven't got time to unpack them. But basically, all the things you're seeing today are using a generic machine learning algorithm called PPO, which stands for Proximal Policy Optimization. It's basically an algorithm that's designed to teach a policy as quickly as possible through gradient descent. That doesn't mean anything to you. It doesn't really matter. It's a generic machine learning algorithm that's really good for a wide variety of uses, but isn't very specialized. It's quite good for playing around in a video game engine. All these parameters tell it how fast it needs to learn, how to update the policy it's learning, how to update the policy it's generating, and what memory it has based on previous actions. So if it did a stupid thing and got an error in one round and then it does it again, sometimes it can know that, sometimes it can't. You can define how it knows that here. So to train it, we run a thing on our command line, which I'm going to go up here a little bit. You can see I've been training it a lot overnight to fiddle. So we're going to go ML agents-learn, NZGDC22, because I don't remember how many. And I'm basically going to point this ML agents-learn command at the ball.yaml file, which I just showed you, and then tell it to run. Once you run that, it gives you a nice, weird ASCII version of the new Unity logo. It used to be the old one, but alas. And we can then run Unity. And then what's going to happen is it's going to take random actions for however long I let it until it converges on a policy. So Unity is just sending completely random actions to that ball, and sometimes the ball is managing to roll its way into the cube. When it rolls its way into the cube, it gets a big reward. When it accidentally rolls off the edge, it gets a big negative reward, and eventually it's going to learn, I should always roll into the cube. And as it trains, you'll see information gets spewed out into the terminal about how it's learning. So that could take about an hour to learn properly. It's a very simple example, but it will still take about an hour. This computer is not very powerful, but on an even more powerful computer, it will still take about half an hour. It can use your GPU if you have one. It's a really good reason to get a good GPU if you're not doing games that need a big GPU. I'm just going to kill that and show you one I've already trained. So if I click the ball agent here, and I'm going to drag this file here. This is a neural net file that gets spit out of that training process. I'm going to put it into this slot here. So I've just assigned that file to that slot. Now, when I run it, you will see it's kind of rolling its way towards the thing pretty consistently. Sometimes it will still fall off because I only trained it for about half an hour, but it will pretty consistently get to the thing. And that's with no actual behavior to do that, which I think is pretty impressive. So I've got about 8 minutes left. I'm going to show you a couple of other quick examples because I think it's fun to see how it works. I'm going to pause that. This is basically that balancing cube, but not cute, because I'm not an artist. So as you can see, I've applied my utmost artistic talent to making this, and it's very beautiful. But this one has a training area again. It has a cube, which is the agent, which I'll get to in a second. It has a ball, which has absolutely nothing special about it, and it has an extra camera. So this extra camera is, as you can see there, it's kind of pointed down at it. In this one, we'll have a look at its agent script for a second. Agent script is here for some reason. This agent script basically says when you start, reset yourself to flat and drop the ball on top of it. And on action received, you can basically jiggle yourself to hold the ball on top. But you might notice it has no collect observations function or method to override. That's because the way it's getting its observations is via the camera. So this agent has a camera attached to it, and this agent has a thing called a camera sensor, which knows about that camera, and that basically uses a render texture of a very small version of that camera to learn the policy. And its policy is to keep the ball on its head, and its only observation of the world is that camera. So it's actually learning based on the vision rather than any number or numerical input you give it. It's obviously turning it into numbers underneath, but it's really cool that you can kind of do it this way. So I'm going to select the agent and drag the balancer into there, which is already in there. This one only trained for about 5 minutes, so it's bad, and you'll see it's bad. I'll show you a good one in a second, and then run that. It's going to try its best to balance that. You know, it's not very good. But I don't think I could keep a ball balanced on my head either, so it's doing its best. I'll show you this exact same thing, but the nice clean version that Unity made. Right, they've all learned how to do it very quickly. So I think that's pretty cool, and it's a really good way to learn machine learning because it's very visual, it's very engaging, and you can probably make some pretty cool stuff for your video games out of this without having to try too hard. You can also mix all these behaviors with heuristic coded behaviors, so you can get something kind of emergent going where it operates more like a traditional AI and then kind of does something a little bit weird. So if you're making a horror game, that might be fun. That's pretty much everything. I'm just going to spend 1 more minute showing you one of the creepy ones. If you have a phobia of like crawly things, might be worth looking away now because this kind of looks like a spider. Some people don't like it. So I'm just going to run this one. This one's the thing that's learned to walk by flinging itself around. It's kind of cute. Remember, there's no animation here. There's only machine learning. And it sort of gets there eventually. I love that Unity gave all them little faces. They're all made up of like basic geometry, but they've put faces on all of them, and I think it's like the friendliest thing Unity's ever done, honestly. Maybe they should do that to their CEO. Anyway, so that's Unity ML agents and machine learning in general. I hope that was of interest to people. We have maybe 5 minutes for questions, and there's 2 microphones. So if anyone has a question, I'm happy to answer it. Otherwise, thank you very much. You can find me on Twitter @ParisBA, PARASBA. I'll tweet some links later about this. Thank you for listening. We have a question maybe. Here, I'll put the worm up in the meantime.
How are you able to take advantage of the GPU or any other services to speed up training?
So I think Unity has some sort of expensive commercial service you can pay for. You can tell I'm not a Unity shill, I just like this. Unity has some sort of expensive cloud service you can pay for to train it quickly. But to their credit, in the GitHub, they also have documentation on how you can very easily spin it up in like AWS or Azure. And it's very cheap to run a training session in the cloud with a really ridiculous GPU for very quickly. But also, if you have an NVIDIA GPU, it will just work. And as of the most recent build of PyTorch, if you have an Apple Silicon device, it will just work on that as well.
Nice. And very briefly, about how long do you think the snake and the spider might have taken to train?
On my 1080, old 1080 Ti at home, it takes about 4 hours to train the snake or the spider to this level.
Impressive. Good.
Yep.
Hi. Do you have any more information about how the image recognition works for the camera? Like, how can it tell when the ball's fallen off the cube's head?
Yeah, so it's using what's called a convolutional neural net, which is basically reducing the picture from the camera to a very small resolution one. You can set the resolution, so in this case it's 84 by 84, I think. And we usually set it to grayscale because it simply doesn't need the color information. And that way, it basically gets a grid of numbers that represents that picture, and some versions of that grid of numbers represent a picture which a human could tell was the ball fallen off. And in that situation, it gets a negative reward. And it slowly learns that when the picture looks like that, that's bad. So it should keep the picture looking like when the ball is on top. And that's pretty much all that's happening. It's reducing it to numbers.
Cool, thank you.
Really cool talk, thank you. I'm not a programmer, so this might be a dumb question. But in terms of training the model, does that all have to happen up front, like before you say release a game, or can it happen while the game's actually out there or people are playing it?
Yeah, you should train the model up front, but you can also update the model live. So it's a little bit out of the scope of the talk, but machine learning models can have certain pathways. They're basically a big network of numbers that it's passing things through. Some of those pathways can be designated as updatable, and you can basically make it get better as it learns more from other behaviors. So yes, you could update it on the fly. That is very complicated though. Yeah. A good example of a model updating on the fly is like how your phone knows what a dog is in photos. The way it does that, at least on iOS, is Apple has a big machine learning model that knows what all these things that you could take photos of are. And when you have a photo of like your dog or your friend Fred, it adds the Fred path to the human and sort of updates it based on that. But it's existing in the same general structure of paths. Yeah.
Makes sense, thank you.
Yeah.
Hi, thank you for the talk. What sort of limitations are there on the type of inputs that the machine learning agent can accept? Because you showed vectors and positions, for example, but could it take input from shaders, for example?
Yep, it can take input from anything. Any number you can send it, it can take an input from. So there's absolutely no limit to what you can do. Unity supplies a really good collection of sensors. Some of them have been contributed by like Ubisoft and so stuff like that who are using it in their games. There's a really good grid sensor, for example, which lets you overlay a big grid on your world. And then it kind of, for the human who's watching, it changes the color of different things that are in the grid so you can see what they are. And it just sends this big grid map back into the AI, so there's like, it knows what type of object is where. It really makes sense to make heavy use of Unity's tags because it can use the tags very well to know what things are. But yes, shaders can definitely send input in. Yeah.
Cool, thank you.
No worries. Anyone else? Nope. Well, thank you for coming and appreciate it.